Hi, this is Jahnavi from ECE-C. My roll number is 24BQ1804G2. My topic is functions of mood. Subtitle Characteristic functions. Functions of moods. To calculate the nth moments of a random variable x, two functions are generally used. Characteristic function, moment generating function. Characteristic function. Definition. For a random variable x with probability density function fx of x, the expected value of E of j omega x is called the characteristic function. Phi x of omega equals to E of e power j omega x. Here, omega is a real variable from the range minus infinity less than omega less than infinity. J is the imaginary unit, j square equals to minus 1. For a continuous random variable, phi x of omega equals to minus infinity into infinity e power j omega x fx of x. For a discrete random variable, phi x of omega equals to sigma I e power j omega xi into p of xi. Properties. The characteristic function transforms the random variable x into another real variable omega. It can be expressed as a Fourier transform of fx of x with the sign of omega reversed. Thus, phi x of omega equals to fx of x are Fourier transforms. Inverse Fourier transform. The probability density function fx of x can be obtained back from phi x of omega using the inverse Fourier transform. Fx of x equals to 1 by 2 pi integral minus infinity to infinity phi x of omega into e power minus j omega x d omega. Summary. Phi x of omega equals to characteristic function of x. It is the Fourier transform of fx of x. Fx of x can be obtained as the inverse Fourier transform of phi x of omega. Hence, phi x of omega and fx of x form a Fourier transform. Theorem. Moments from characteristic function. If phi x of omega is the characteristic function of a random variable x, then the nth moment of x is given by m equals to minus j power n d power n phi x of omega by d power omega n equals to from the range omega equals to 0. Step 1. Characteristic function definition. From a random variable x, its characteristic function is phi x of omega equals to e of e power j omega x. Step 2. Series expansion of e power j omega x. The Taylor series expansion is e power j omega x equals to 1 plus j omega x plus j omega x whole square by 2 factorial plus j omega x whole cube by 3 factorial plus and so on plus j power x whole power n by n factorial plus and so on. Step 3. Substitution into expectation. Taking expectation, phi x of omega equals to e of e power j omega x equals to 1 plus j omega e of x minus omega square by 2 e of x square minus j omega cube by 3 factorial e of x cube plus and so on. Thus, phi x of omega equals to m0 plus j omega m1 minus omega square by 2 m2 minus j omega cube by 3 factorial m3 plus so on, where mn equals to e of x power n is the nth moment. Step 4. First derivative. Differentiate with respect to omega. D phi x of omega by d omega equals to jm1 minus omega m2 minus j omega square by 2 m3 plus so on. At omega equals to 0. D phi x of omega by d omega, where omega equals to 0 equals to jm1. Hence, m1 equals to minus j of d phi x of omega by d omega, where omega equals to 0. Step 5. Second derivative. D square phi x of omega by d omega square equals to minus m2 minus j omega m3 plus so on. At omega equals to 0, d square phi x of omega by d omega square, where omega equals to 0, equals to minus m2 equals to j square omega m2. Thus, m2 equals to minus j square d square phi x of omega by d omega square, where omega equals. Step 6. Generalization. By continuing the differentiation process, the general form is d power n phi x of omega by d omega whole power n, where omega equals to 0 equals to j power n mn. Therefore, mn equals to minus j whole power n d power n phi x of omega by d omega power n, where omega equals to 0. Properties of the characteristic function. The characteristic function is unity at omega equals to 0 and given by phi x of omega, where omega equals to 0 equals to phi x of 0 equals to 1. Proof. The characteristic function is given by phi x of omega equals to e of e power j omega x. At omega equals to 0, phi x of 0 equals to e of e power 0 equals to e of 1, that equals to 1. Second property. The maximum amplitude of the characteristic function is unity at omega equals to 0. That is, mod of phi x of omega less than or equals to phi x of 0 or mod of phi x of omega less than or equals to 1. Proof. Let the characteristic function phi x of omega equals to e of e power j omega is. The amplitude of phi x of omega is mod of phi x of omega equals to mod of e power j omega x. Mod of integral minus infinity to infinity fx of x e power j omega x dx. Since mod of xy less than or equals to mod of x mod of y. Mod of phi x of omega less than or equals to integral minus infinity to infinity mod of e power j omega x into mod of fx of x dx. Mod of phi x of omega less than or equals to integral minus infinity to infinity mod of fx of x dx. Since mod of e power j omega x equals to 1, therefore mod of phi x of omega less than or equals to 1. Third property. Phi x of omega is a continuous function of omega in the range minus infinity to omega less than infinity. Proof. We know that phi x of omega equals to integral minus infinity to infinity e power j omega x into fx of x dx. Since omega is continuous, e power j omega x is also continuous. Hence, phi x of omega is a continuous function. Fourth property. Phi x of minus omega and phi x of omega are conjugate functions. That is, phi x of minus omega equals to phi x star of omega. Phi x star of minus omega equals to phi x of omega. Proof. We know that phi x of omega equals to e power j omega x. Phi x of minus omega equals to e of e power j minus omega x. Phi x of minus omega equals to e of e power j minus omega x. Phi x of star minus omega equals to e of e power j minus omega x star. Phi x of minus omega equals to e of e power minus j omega x equals to e of e power j omega x star. Phi x star of omega equals to e of e power j omega x. Phi x of omega equals to phi x star of omega. Therefore, phi x star of minus omega equals to phi x of omega. Thank you.